Hello everyone, welcome to lecture 25 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on different types of engineered metamaterials and their applications. So, here is the lecture outline. We will talk about chiral metamaterials and their applications, introduce biisotropic and bianisotropic metamaterials. We will discuss about non-resonant metamaterials and their applications, and briefly we will touch upon hyperbolic metamaterials and also show their different application scenarios. So, chiral metamaterials, okay, we have seen that chiral metamaterial sensors using split ring resonators with double splits, okay, they are also known as SRDS, okay, split ring with double slit, okay, or double split. They have shown sensing capabilities in the X band. Now, the resonance frequency of the chiral metamaterials based SRDS sensor is linearly related to the permittivity and the thickness of the sensor layer, which creates a suitable approach for sensing environment and organic parameters. So, when the sensor layer is filled with related material, changes in the tissue temperature, sand humidity, then the calcium chloride, lead density, all these things can change the resonance frequency and that can be detected. Other potential sensing applications include sensing of pressure, temperature, humidity, moisture and density. So, you can also have sensor for these applications or sensing these parameters. Now, chiral metamaterials are also very useful in nonlinear optics. Okay. So, the chiroptical properties will see that can give rise to second harmonic generation, and typically these are often much stronger than in the linear regime. Now, why we are interested? Because in the case of biochemical engineering, the chiral applications, okay, they can extend beyond the linear regime. So, you can actually have this kind of nonlinear effects like second harmonic generation happening. Now, in the second harmonic generation process, two photons at fundamental frequency annihilate into one photon with double the frequency, right. So, the second harmonic generation basically requires a non-centrosymmetric media that lacks inversion symmetry, and chiral metamaterials are naturally suitable for this kind of application since they are intrinsically non-centrosymmetric. Now, the detection of chirality, or you can distinguish the chirality with linear polarized light regardless of the polarization direction and the state of the second harmonic light output. Okay. So, linear optical responses in chiral metamaterials are reciprocal, and nonlinear responses like second harmonic generation are basically non-reciprocal. So, this is what we need to keep in mind. Now, with that we can go ahead and try to see different chiral material interaction with light. You can also call it as chiral light matter interaction. So, the main goal, one of the main goals of this chiral metamaterial is to basically enhance this chiral light matter interaction. So, superchiral fields are basically employed to overcome weak chiroptical signals in nature. So, you will see various nanostructures are developed to enhance these chiroptical signals, such as plasmonic nanostructures, dielectric nanoparticles, and also negative index metamaterials, right. So, the interaction between the quantum emitter and chiral metamaterials have been experimentally investigated, and you can see in this particular figure that here chiral arc metamaterial are basically adopted as two enantiomers, enantiomer A and B. So, there is slight variation, one is kind of the mirror image of the other, okay, and you can see that achiral quantum dots are basically predominantly surrounding the upper arc of the metamaterials. So, these are enantiomer A and B of the twisted arc chiral metamaterial, and these are very useful for chiral light matter interaction. So, we will see that how the light matter interaction basically changes because of this structure. Now, in the linear regime, you can see that the chiral dichroism of the arc metamaterial reached as high as 50% at the wavelength of resonance, that is around 780 nanometer, which can lead to very strong contrast of the transmission images that you can see in this figure. And here we are particularly showing the E square enhancement in both the cases. This is for enantiomer A, this is for enantiomer B under LCP and RCP light. So, this one is LCP, this is RCP. You can see the dark one LCP and RCP. So, there is a difference, and that is shown here. These are basically simulation data. So, this is for enantiomer A, that shows substantial enhancement of the intensity within the surrounding region of the chiral arc. You can see from these field plots as well. At 800 nanometer under RCP, you have more field enhancement over here, which is basically seen here also. The same thing is shown here, but here you can see the enhancement is basically seen in the case of LCP, which you can also see from the electric field plot. So, what we understand that the light confinement at the resonant wavelength was largely boosted, and thereby you have got this chiral selective enhancement in the nonlinear light matter interaction. So, in this case, for the case of enantiomer A, RCP is showing the enhancement. In the case of enantiomer B, LCP is showing the enhancement. So, this basically manifests the potential for application of this kind of chiral metamaterials in chiral selective imaging, then sensing, spectroscopy, etc. So, now let us look into active chiral metamaterials. Now, active control over the chirality of metamaterial has the potential of serving as one of the key element for the future optical systems, such as polarization, sensitive imaging, and say interactive display and so on, right. So, achieving active control over chiral metamaterials involves the reconfiguration of the metamolecule from a left hand enantiomer to a right hand counterpart and vice versa, right. So, you have to involve that switching, right. So, in the terahertz regime, the generation of charge carriers via optical pumping in silicon is basically used to switch this chirality. You can also think of a laser pulse working at 800 nanometer is utilized to excite the electron hole pair across 1.12 electron volt band gap, that is of the electrons, and then under the illumination of a 500 milliwatt pump laser, the silicon's photoconductivity can reach as high as 50,000 Siemens per meter. So, this feature basically enables all optical switching of the handedness in chiral metamaterials in terahertz regime. So, an all optical tunable chirality has also been realized in a double layer metamaterial, which basically consists of a nonlinear nano auto AU, nano AU colon ITO, that is basically this structure. So, you can see the structure here, that is having a ITO layer in between two L shaped gold nano antennas. So, these are the two L shaped gold nano antennas, and you have ITO here, and this is your silica substrate, right. So, what happens in this case, one can observe a 45 nanometer shift in the peak when you are looking at the circular dichroism spectrum, under 40 kilowatt per meter square, 40 kilowatt per centimeter square kind of pump. So, that is typically a weak pump, and this work basically opens up the possibility for ultra low power as well as ultra fast all optical tunable chirality at optical frequencies. So, you can see the wavelength range here. So, you are basically tuning the chirality in the visible range. Now, we move on to another type of metamaterial, which is biisotropic and bianisotropic. Okay. So, what are this? In physics, engineering and material science, a biisotropic material is basically an isotropic material where electric and magnetic flux densities are linearly coupled to both the electric and the magnetic fields via scalar constitutive relations, okay, including magneto-electric coupling terms. Okay. So, a major subset of this kind of material, also known as Pasteur media, they can rotate the polarization of the light in either refraction, that is like transmission, right. So, not all materials with a twist effect basically fall in this biisotropic class. The twist effect of the class of biisotropic materials is basically caused by the chirality, okay, that is kappa non-zero, okay, and or their non-reciprocity, which is given as non-zero chi. Okay. So, that all depends this non-reciprocity of the structure, right, of the media in which the electric and the magnetic field of an electromagnetic wave, or you can say simply light, interact in a very unusual way. Now, if you move on to the next term, that is bianisotropy, that are a type of electromagnetic material where electric and magnetic fields are basically coupled, and an electric field here can induce a magnetic response and a magnetic field can induce an electric response, right. And this coupling is basically described by constitutive relations that include magneto-optic coupling terms, making them distinct from simpler materials like isotropic or anisotropic materials. So, when we talk about bianisotropy, so that basically implies dual polarization mechanism, and also there is a inbuilt anisotropic behavior, right. So, for most materials, the electric field E and the electric displacement field D, okay, as well as if you talk in terms of the magnetism. So, you have a magnetic field B and the inductive magnetic field H, they are basically parallel to one another, but like those kind of materials are known as isotropic medium. But for some complex materials, such as in many metamaterial, you will see that these fields are not necessarily parallel. Okay. So, that is the case when you can call them like these materials are anisotropic, right. So, when they are parallel, you call them isotropic. When they are not parallel, this kind of materials, you call them as anisotropic. Fine. So, now let us look into the historical context of this kind of material. So, although the first known study on the biisotropic materials dates back to 1811, when Francis Arago observed the rotation of polarization, or you can say the polarization plane of linearly polarized light in quartz. The general properties for the fields in biisotropic media were recognized far later, only in 1970s. Okay. So, you can see the gap between these two studies. Okay. The wave propagation in such media was studied thoroughly only in 1990s. Okay. So, during the last decade, the interest in this bianisotropy has resumed thanks to the unique opportunities it provides for the design of metasurfaces, where you can control the optical activity, asymmetric absorption, reflection, one-way transparency, anomalous refraction, etc. So, when you want to do more peculiar stuff in terms of electromagnetic response of your material, you can use this kind of bianisotropic metamaterials. So, you can take a simple example of a split ring resonator. You can see this is the split ring. Okay. So, here what you can see that in addition to the electric and magnetic polarization, so this is the incident external electric field, this is the way it is polarized. So, you get a polarization like this, there is a polarization current. So, there is a current density, okay, that gives you a magnetic dipole moment in this direction, right. So, this is how the a metal split ring resonator is positioned in an external electric field distribution, right. Now, what you see here is that in addition to the electric and the magnetic polarization, this split ring resonator also possesses bianisotropic response. How? Like, you have to understand that the electric field E external here is basically exciting the magnetic dipole moment M, isn't it, because of this current that is flowing through the loop. Now, since the resonator size is comparable to the wavelength, the induced polarization current J is non-local. That means, it depends on the external field in the whole volume occupied by the resonator, okay. And due to the geometry of the split ring, the electric field also excites both, you also get a polarization because of the charge splitting. So, you get both electric and magnetic dipoles, right. So, it becomes very interesting, and a simple split ring resonator has got electric and magnetic as well as bianisotropic response. Now, the magneto-electric cross coupling means that in addition to the permittivity epsilon and permeability mu, you got to now study a parameter that measures the strength of the chirality kappa, and then you also need to study the Telegan parameter chi, okay, that measures the non-reciprocal magneto-electric coupling, which also affects the wave phase. Okay. So, here you can see on the figure that shows the division of isotropic media into 4 classes depending on whether epsilon or mu are positive or negative. So, this is the effect of chirality on the backward wave characteristics. So, you can see this is the axis epsilon and this vertical axis is mu. So, here both are positive. So, you get a forward wave. Here you get negative epsilon and positive mu. So, you do not get any propagation. Here also you get positive epsilon and negative mu. So, you do not get any propagation, but here both epsilon and mu are negative. So, you get a propagation, but that is a backward direction. So, you get a backward wave. So, what you understand is that wave propagation requires epsilon and mu to be of the same sign. So, the double negative media basically supports backward wave. Now, however, when the chirality parameter is allowed to be non-zero, that is kappa is non-zero, the situation is basically characterized as shown in this particular figure, where we for simplicity considering that the Telegan parameter chi is 0. Okay. So, what is this figure telling us? It shows the effect of chirality on the backward wave characteristics of the biisotropic media when you are considering epsilon and mu to have the same sign, and we are considering a special case where kappa equals 0. Okay. So, this is important. So, we are considering epsilon and mu to be of the same sign. So, the square root will basically take the sign of these two parameters. So, kappa, which is calculated as square root of epsilon mu. So, if both are positive, so kappa is also positive. If both are negative, so kappa will also be negative, right. So, depending on this kappa, the medium can then support 2 forward waves. Okay. So, here you can see you get forward waves here. Okay. Here you can get backward and forward. Here you can get forward and backward. Here you can get backward, right. So, these 2 waves are like basically depending on the magnitude of the chirality parameter, that is kappa. So, you are getting 2 eigenwaves, okay, which can be forward. In that case, the wave vector amplitudes are both positive, or you can have both backward. So, in that case, both wave vector amplitude will be negative, or even you can have waves with one positive and one negative, right. So, all these possibilities are there. So, what are the key implication here is that a negative index media can exist without double negative epsilon and mu. Okay. So, that is the understanding here. So, you can say a corollary that in order to create negative index medium, that means a media that supports backward wave. So, it is not a necessary condition to have double negative material, right. So, we can see that a sufficiently large chirality parameter, when your kappa is much larger than square root of epsilon and mu, that can also induce backward wave behavior, right. So, this is something very new, and you can see that if you have very small values of very small absolute values of permittivity and permeability, that can give you some interesting possibilities in the connection of chirality, where you can also see backward wave, right. So, you need to understand the extreme case in this respect is the so called chiral nihility, that means where the chirality will disappear, right. So, that is the special case where epsilon mu becomes 0, but your kappa is non-zero. That means the medium will still possess a non-zero chirality parameter. So, that enables wave propagation solely because of the chirality, right. So, here you can see the interrelation of the domains of backward wave media and the 4 subclasses of biisotropic materials, right. So, what we are considering, all are basically negative index medium here. So, you can think of 4 categories, something like reciprocal. So, when it is reciprocal, so chi equals 0, and then so this one is reciprocal and non-chiral. So, you have ordinary isotropic medium. So, you can write them as chi equals 0, kappa equals 0. So, there can be reciprocal chiral medium, which is basically the passive medium. So, chirality parameter is non-zero. So, you have kappa non-zero, but reciprocal, so chi equals 0. On the other hand, you can have non-chiral but non-reciprocal also, that is the Telegan medium. So, that is typically chi not equals 0, but kappa equals 0, and then you can have non-reciprocal and chiral. So, this is the general biisotropic media where both are basically non-zero. Okay. So, negative index media are possible across all these subfields, okay, of biisotropic materials, including the chiral, which are handed mediums. Okay. Something here we have seen, these two are the non-chiral mediums. So, there is no handedness. Then you can also have this in reciprocal and non-reciprocal kind of medium. So, negative index medium is possible in all these different category. So, negative index media is the media where a plane eigenwave can exhibit backward propagation. That means it has got a negative phase velocity, and that can be possible across all these different subfields. So, now let us look into non-resonant metamaterials and their applications. So, anisotropy basically refers to the variation of material properties based on direction, and you can classify this into uniaxial anisotropy that involves one unique direction, which is also known as optic axis, that affects the material properties. It can also be classified into biaxial anisotropy that involves 2 distinct directions influencing the material's behavior. So, uniaxial will have only one optic axis, biaxial will have two. Okay. So, we have seen this particular geometry earlier. So, why we are showing it again? Because this is a stratified metal dielectric composite. If you recall this figure, this is nothing but a layered metal dielectric structure, where the permittivities of the two constituents are given as epsilon 1 and epsilon 2. Now, for the two components in this multilayer stack, if we consider the volume fraction of material 1 is F1 and for material 2 it is F2, F2 is nothing but 1 minus F1. In that case, you can say that the effective permittivity along the two principal polarization, that is when the electric field is polarized along the plane of the interface, that is epsilon parallel, it can be this direction or this direction, this or this, that can be given as epsilon 1 epsilon 2 divided by, epsilon parallel can be simply written as F1 epsilon 1 plus F2 epsilon 2, and epsilon perpendicular is when the electric field is polarized normal to the interface. You can write epsilon perpendicular equals epsilon 1 epsilon 2 divided by F2 epsilon 1 plus F1 epsilon 2. Now, the extraordinary axis is basically aligned perpendicular to the plane, and the ordinary axis, as you can see in this two direction, the permittivities are same. So, you can consider them as ordinary axis. They are basically aligned parallel to the interface, right. So, this is basically a uniaxial stack. Now, for this kind of uniaxial stack made of nano-layered metamaterials, the effective permittivity tensor is basically a diagonal matrix that can be written as this. So, you can write epsilon effective will have epsilon parallel in the two direction, and then you have epsilon perpendicular in the other direction, right. So, this is the extraordinary refractive index or permittivity, this is along the ordinary ones. So, you can also write them as epsilon O that is ordinary, epsilon E that is extraordinary. Now, this we have also seen earlier that if there are more materials, so you can actually still find out the epsilon parallel based on the summation of I over Fi. Fi is the volume fraction of each material that has got a permittivity of epsilon I, and you can find out the perpendicular component as 1 by epsilon perpendicular will be summation over I Fi divided by epsilon I, right. So, for some applications you can see that you can actually make artificial wave plates, okay, that can be made in this kind of geometry. You will see that the wave plates basically rely on the difference between the values of these two permittivity, extraordinary and the ordinary. Now, the strength of anisotropy is also called the birefringence, because you see two different refractive index values in two different directions. So, you call it birefringence, bi means 2. Okay. So, the strength of anisotropy can be calculated as delta epsilon, which is basically the difference in between epsilon E and epsilon O. Now, if the difference is positive, you call it as a positive uniaxial metamaterial. If the difference is negative, you call it as a negative uniaxial metamaterial. So, usually a stack of dielectric alternative layers are used to design negative uniaxial metamaterials, okay, because in this case you will get epsilon O is larger than epsilon E. Okay. So, there are different geometries people have tried. Okay. So, here a lot of these geometries are shown. Always remember, the dark color shows the material with higher refractive index, and lighter color shows the lower refractive index. So, here it is like dielectric material and air. Okay. So, you can see that people have made a lot of positive uniaxial materials using array of blocks, which can be either cylindrical or of square cross section. So, these are square cross sections and these are of cylindrical unit cell. Okay. There are other designs. So these are actually of the real blocks. So these are dielectric rods. Okay, the top view you are seeing, so it looks like a circle. This is a square rod. Okay, so you are looking from the top. This is, these two are square arrays, and these two are basically hexagonal array. So this is a hexagonal lattice, or you can say hexagonal array of circular rods, dielectric rods in air. This is a hexagonal rod, hexagonal array of hexagonal rods in air, and these are the complementary structure. That means in a dielectric slab you are making a circular hole or a square hole, or you are making holes in the form of rectangular lattice or so on. Now why people have tried so many different structure is to see where they get higher anisotropy. So it is found that hexagonal arrays produced stronger anisotropy than square arrays due to their greater packing density. That makes sense. Okay, and of all these combinations you will see that the hexagonal array of hexagonal shaped rods, so this one suspended in air, so this is the one that has given the highest birefringence. So this is a clear winner. Okay. Now there are some challenges, that hexagonal shaped rods are not that easy to manufacture. So people usually go with hexagonal array of circular rods because these are easy to manufacture, right. Now considering the ease of fabrication and design, the final design that people go with is that hexagonal array of circular rods. Okay. So people do a double parameter sweep to determine what should be the radius of the rod and the thickness of their support, because you cannot have all the rods suspended in air, then the entire structure will fall down, right. So you need this kind of supporting structures that will connect one circular rod to another circular rod, but obviously it is clear that you want this to be as thin as possible. So this kind of a study that plots the thickness of the supporting rod T by A is basically the lattice period, and then here you have R by A. So this is the normalized plot, shows you that the maximum anisotropy can be achieved here when the radius is 40% of the lattice period, but you need to go for thickness of the support rod as minimal as possible. So here in this case the dielectric was chosen to be polycarbonate, which has got a dielectric constant of 2.57. Okay, and the whole idea is that you need to keep the supporting rod as small as possible while it is still mechanically robust. Okay. So the final the optimal value was found to be 0.42A exactly here. Okay, and these are the values of the dielectric tensor that was calculated. So you get actually 3 different values in 3 different directions. Right. Ideally these two should have been same, but because of the rod they show up some kind of different values. Okay, but this is the constituent material, but you can see here you are getting anisotropy, okay, because of this. So these are the final dimensions that has been used, and people have fabricated this in different directions, and in three different orientation it has been printed for testing, and you can see that they show much better results. So the simulated value actually showed very different result, but when they measure it they could see that that rod has got very minimal effect, and these two values are very close to each other, and that is what was expected, right. So they show a very good result towards this uniaxial metamaterial, right. So the final thing will be discussing today is this hyperbolic metamaterial. Why we are considering this? Because hyperbolic metamaterials are known to have very high anisotropy. These are also uniaxial materials that have got hyperbolic dispersion. So here it is basically you have hyperbolic metamaterials which act like a metal for certain polarization, or you can say direction of light propagation, and they behave like dielectric for the other, right, because you have got negative and positive permittivity tensor components that gives you extreme anisotropy. So, here the figure basically highlights various phenomena and applications of this hyperbolic metamaterials, something like super resolution imaging, ultra fast light sources, second harmonic generation, spontaneous emission enhancement, compatibility with rollable platforms, and also unidirectional transport, right. So, as you can see that hyperbolic metamaterials have got some peculiar characteristics, because here the dispersion relation in the wave vector space actually forms a hyperboloid, okay, and that is why they are known as hyperbolic metamaterials, and there you can have a lot of interesting applications. We will take up this later on. I am just mentioning about them here because in the context of anisotropic metamaterial, they are also a very they are promising candidate, because they have applications in sensing, reflection modulation, or all optical ultra fast switching. Okay, you can also use them for integrated photonics and imaging, right. So, we will be discussing hyperbolic metamaterials in details in this course later on. So, for this lecture we will stop here, and we will continue our discussion with a magnetic metamaterial which is based on split ring resonator in the next lecture. So, if you have got any query regarding this lecture, drop an email to this email address mentioned in the course title and the lecture number on the subject line. Thank you.